Now, why is the characteristic function so very important? Because of two results. Here is result number 1. If we have two random variables x and y whose characteristic functions match over entire R, then they must have the same distribution. So it is much like the CDF. If CDFs match, then they must have the same distribution. And also like CDF, it must exist for any type of real valued random variable. We are not going to prove this. This proof is not entirely easy. You will see it in your probability 3 course. Now the second result is what makes it useful. If I give you some exercise independent and you are interested in the linear combination summation ai xi, ai's are real numbers, then you can easily find out the characteristic function of the linear combination from the characteristic function of the individual xi's, and this is the relation. All that you do is you take the characteristic functions of the individual xi's, evaluate them at ait and take the product. And the proof of this is pretty straightforward. I will just write J for the subscript so that I do not confuse this subscript I with the complex I. Then this quantity is just from the definition e to the power I times the random variable and t. Now you can easily see that this thing just is a product of all the exponentials. Now I have told you that the xi's are independent, so these things being function of the xi's, they are also independent. Expectation exists finitely, so you can write it as product of the expectations. Now this is very much like our characteristic function, except that the role of t is being played by a1t here and ant here. So these things are nothing but xi x1 a1t. Similarly, this will be xi xn ant, and that product is precisely what I have written over here. The way to use this theorem is to have a list, a ready-made list of the characteristic functions of lots of known distributions. We are going to learn such a list. Then, whenever xi's have distributions in that list, you will know these things, form the product and check if this is also in your list. If it is in your list, then immediately you will know the distribution of the linear combination of the x's. We will see this in action later once we learn about some standard distributions. Suppose I give you a family of densities. I tell you all these things are densities when A is positive. So F1 is a density, F1.5 is a density. The densities all have the common form. X to the power a minus 1, e to the power minus x. The constant is whatever is needed to make the total integral 1. Now I tell you that this density corresponds to the characteristic function 1 by 1 minus it to the power a. So if you integrate e to the power I xt times fax, you will get this. So you do not have to do it. I am telling you that this is a standard result. Use this standard result to do the following. If I give you 3 random variables x, y, z such that x has density fa, y has density fb, z has density fc, of course abc are all positive because that is the restriction. Your job is to find the density of x plus y plus z. You can of course use that sum formula twice, so you have to do 2 integrals. But here what you should do is you work out the characteristic function of x, characteristic function of y and characteristic function of z. Since they are independent, the characteristic function of x plus y plus z will be the product of the 3 characteristic functions. And immediately it will be of this form, and from that you can get the corresponding density.